Hey there, math physics students. Mr. Simon coming at you again. I created a video that has a couple of the free body diagrams that we did not get to in class. So the previous video I have has some of the problems on page 62, number 3 and 4, and on page 63, number 5. Today I'm going to do a video on how to do the last one on page 63, the incline plane problem. This is by far the most challenging of all the problems. So we don't always get to this even in a non-COVID online year. But it's a good one to get to know how to do because we are often on inclined planes. Anytime we bike up a hill, bike down a hill, go skateboarding, go for a run up a hill, drive up a hill, ski down a hill, we're always going up and down hills. The physics behind it is a little bit more complex, however, than the previous couple free body diagrams. This problem is different than problem 3 on page 62. It often gets confused. It's an angle problem. They all work the same. Not really. Number 3, which is on the previous YouTube video, is an object being pulled at an angle. So my force is at an angle, but it's still moving in the horizontal or X direction. So we're pulling at an angle, but it's still moving on a regular horizontal surface. What makes number 5 on page 63 more difficult is I'm actually going at an angle. So I'm actually going not in the horizontal or vertical direction. And that's an inclined plane problem like we're about to do. So we're biking up a hill. First thing to do this problem is we have to change our normal XY coordinate system. So normally we live in a world and we denote vertical and horizontal and or Y direction and X direction. We're going to take our normal XY coordinate system and tilt it to the incline that we are biking. In other words, I'm going to take a dotted line and adjust my world from my normal XY coordinate system to one at an angle. So I'm going to adjust my X axes to be at an angle. And then obviously perpendicular to that, so it will be the Y axis. So this is my new X axis. This is my new Y axis. And I'm just tilting the world in which we live. Now the way I'm biking is along that new X axis. So that's the first key to doing an inclined plane problem. So now let's draw a free body diagram. So remember, a free body diagram is a simple sketch showing all the forces acting on an object. So for my free body diagram, I don't spend time drawing a piano, a bike, a car, I just draw a little box. So there's my bike, me biking up the hill. And like all the other free body diagrams, the very first force we can draw on every single free body diagram is the force of gravity, otherwise known as the weight. And we know that the weight or the force of gravity points straight down to the center of this earth. We also know that my weight or force of gravity is something the mass times 9.8. So my mass is 90 kilograms. So I'm going to take 90 times 9.8. I'm going to get 882 newtons. So this is my first force. Now, if you remember, on most free body diagrams, right after we draw the weight, we draw the normal force going straight up. The normal force being that support force of the bench, the table, the counter, the floor. But I did say in the last video and in class, anytime things are at an angle, normal force and weight are not going to be equal to each other. You'll see why in a little bit. So I'm going to put a little timeout on that normal force and come back to it later. So let's look at the other forces. Well, I am pedaling up the hill. So this is the way that I'm moving and getting my initial acceleration. So I'm going to be pushing up the hill. I can either draw a vector pulling away or pushing up. I'm going to draw one pushing up. So here's my force as I bike up the hill. I'm exerting a force of 550 newtons. We also know that any direction we are moving or accelerating, that friction is going to act against us or in the opposite direction. So friction, force of friction is going to be going in the opposite direction. Now we weren't given the force of friction, but we were given the coefficient of friction. So remember that little equation for the friction force is the coefficient of friction, that little Greek letter mu, times the normal force. Well, I don't know the normal force just yet, but once I find the normal force, I'll multiply that by 0.4 and I'll get the friction force. There are, in essence, 4 actual forces acting here. There's gravity pulling me down. There's a normal force which is going to be pushing in this direction. Remember why we use the word normal force. The word normal refers to a line in a plane. And normal means that the line is going to be perpendicular to all points on the plane. So normally the normal force is going straight up because we are on horizontal surfaces often. Floors, shelves, countertops. But here we are angling my support surface, so the normal force is going to angle as well. So when we do draw the normal force, it will be in this direction, because by definition it has to be perpendicular to the plane. Here's how I find the normal force. Of my forces, the normal force, friction, pushing, gravity, 3 of them are in the nice XY coordinate system, my new XY coordinate system. That's nice along the x-axis, that's nice and along the x-axis. The normal force will be nice and along the y-axis. But my weight force, my force of gravity, that's the oblique force. So that's the force where I'm going to have to divide it into its components, which is key when you have a force at an angle. So the components are, again, the parts that make up a vector. So properly dividing this into the components would look like this. Where the components, by definition, have to have the right angle between those. Components are the parts that make up that vector. Back when we were doing this in vectors in Unit 2 in my class, I often would use analogies like the components are us driving our car over to Grandma's house, where Uncle Charlie flies a helicopter, he can go in a straight path. I can find these components out because this angle is always going to be the angle of the inclined plane. It's a very simple geometric proof. A little exercise, you see if you can prove why that's always the same as an incline. So that's 10 degrees. I'm going to call this my x component of the weight, W sub x, because it's in my x direction. And I'm going to call this one my y component of the weight, because it's the component in the y direction. And again, the components by definition make up the right triangle. So I can find these using sine and cosine. W sub x is the opposite side of 10 degrees. Opposite side is the sine, so I take the sine of 10 degrees times the hypotenuse. Now a lot of times we associate sine with y and cosine with x, and that's like when you're doing unit circle and stuff, but not with right triangles. Sine is for the opposite side, the old SOHCAHTOA thing. So if I take the sine of 10 degrees times my hypotenuse, 882, I get 153.2. Likewise, W sub y is the adjacent side. So for W sub y, I'm going to use the cosine of 10 degrees times the hypotenuse. So cosine of 10 degrees times 882. I get 868.6. You can always double check these components by doing the Pythagorean theorem. That squared plus that squared should equal that squared, and I'm confident they will. So when I draw my components of my weight vector, and this is true for any time I draw components, I am effectively replacing this force with the two components. It's like that isn't even there anymore. That force is gone, and it's replaced by these two guys right there. Once I get the components, now I can actually draw my normal force. My normal force is going to be equal and opposite of W sub y. So there's my normal force. It's going to be equal and opposite of W sub y. In this case, 868.6 newtons. Here's why. I know that when the bike goes up the hill, it's not going to rise into the air, it's not going to sink into the ground, it's not going to move in my new y direction. So if there's no movement or acceleration in the y direction, there can be no net force in the y direction. Which means these two forces have to cancel out, so there's no net force in the y direction, therefore producing no acceleration in the y direction. Again, this force isn't there anymore. So it's like I have 1, 2, 3, 4, 5 forces left over. 2 of them are in the y direction, they're going to cancel each other out. So once I get W sub y, I just found the normal force. Once I find the normal force, I can find the friction force. So my friction force is equal to 0.4, the coefficient of friction, times the normal force of 868.6 newtons. That gives me 347.4. So that's the trick to doing the problem. It's this whole weight vector, it's tilting the axes, it's finding these two components, these two green components, using sine and cosine to find out the components, then finding the normal force, and once the normal force, the friction force. That's obviously the little twist. And that can be a little bit difficult. These are not easy problems. I now have all my forces solved for. All the values are on there, with all the proper units. I do one last look, make sure I didn't forget any forces. Nope, I think I got everything on there. We are good to go. So now I'm going to net up the forces in the x direction to see how this mass is going to accelerate. As you know, I like to write not just F net equals ma, I like to look F net in what direction are we moving? What direction are we accelerating? We are accelerating in the x direction. Hence why I like to draw those little vectors to show us which way we're accelerating. Which means of all the vectors, all the forces, all the angles all over the place, I only care about the x ones because it's only accelerating in the x direction. I don't give a rat's butt about anything that's not in the x direction. Quick question for you. How many x forces are there? We got arrows all over the place. How many x vectors are there? If you said 2, you're wrong. It's actually 3. So people see these two forces, but don't forget about that guy down here. He's hiding down there, but he is an x force. There's actually 3 x forces in this case. So my net force is my force of me pedaling minus the friction force minus W sub x. Notice it's going against the direction we are going. So it's very common to forget about W sub x because it's hiding down here. Don't forget about W sub x. W sub x is actually a really important vector. It's W sub x that always makes it tougher going uphill and easier going downhill. W sub x is always pointing downhill. If you were going downhill skiing, I love the downhill ski. I don't get to go very often. You're downhill skiing, swishing down the mountain. If you were to stop halfway down and ask some other skiers, hey, what's pulling us down the hill? They'd all say gravity. They'd be partly correct. What's actually pushing us downhill or pulling us downhill is W sub x, the x component of gravity, the x component of our weight. Because by Newton's second law, acceleration has to be in the same direction of the force. So if I'm accelerating down an incline, it's got to be a force down that incline. So technically, W sub x pulls us downhill. Why is it hard to bike uphill? Because you have to battle against W sub x. Why can you coast downhill in your bike? Because W sub x is pulling you downhill. W sub x always pulls downhill. You go cross-country running and running up the hill, it's so tough because you have to overcome W sub x. Then you go running downhill, you can go a lot faster because W sub x is now pulling downhill. It's always pulling downhill, but now you're going downhill. It's a really important vector, so don't forget about it. Common mistake to forget about. So I got my force minus minus. They're going in the opposite direction that we are moving. So I got 550 newtons. The friction force is 347.4. The x component of my weight is 153.2. The mass is 90 kilograms, and we're looking for the acceleration. So I got 550 minus 347.4 minus 153.2 for grand total net force of 49.4. Give or take a little bit for rounding, obviously. So I got 49.4 newtons equals 90 kilograms times A. Divide both sides by the 90 kilograms. I get acceleration to be 0.55 meters per second squared. There you go. Obviously a trickier problem. And even in a regular non-COVID year, we don't always get to this problem. Those of you that take advanced physics will be doing these type of problems in advanced physics. So, one last thing. If you remember, when we talked about free body diagrams, I stressed make your free body diagram big. It shouldn't be a little diagram over here. Make it big so you can show all the forces and all your calculations right on the free body diagram. In fact, the reason to make it big is that's where all the work is. That's where all the thinking is. That's where all the calculation is. In fact, one could say, with a problem like this, there's so much going on here and so much time spent here that once you're done with the free body diagram, it's all downhill from there. Get it? Downhill? See what I'm saying? Yeah. So there you go. That's an inclined plane problem. Again, we didn't get to that this year. And feel free to copy that in your book and hopefully made a little bit of sense. Other than that, you guys, I can't wait till the day where we're all back in school. I'm sure you're the same way. So lots of love to all you guys out there and gals out there. Hope you're doing well. Peace out.